Very good morning to all the people present here physically in the lecture hall and those watching online. My name is Agastya Vishwanath and I am going to be your lecturer and professor for this series of lectures on calculus. Remember that these lectures are both in association with the Lancerian Society of Mathematics and Physics and the Y Project. That being said, this lecture is lecture number 1 and as you can see it's entitled Understanding Derivatives. Now of course, as I explained in the introduction, there are two types of calculus mainly. Differential calculus and integral calculus. We are going to be dealing, at the beginning at least, primarily with differential calculus before inevitably moving on to integral calculus. And one of the most important aspects of differential calculus is the derivative. It is indeed the first thing that you need to understand if you want to get a good understanding of differential calculus. And that's what the purpose of this lecture is. It's to gain a better understanding of this all-important idea, the derivative. This lecture will not be talking much about the mathematics behind the derivative and the infrastructure which we make use of to sort of bring the derivative to life mathematically. That will be the next lecture. This one will be focused, as the name indicates, on understanding what a derivative is. Because I've seen a lot of students learn how to compute derivatives, learn the math behind it, but not get a good conceptual or intuitive understanding for what the derivative is. And not only do they suffer in their learning experience, but they don't know how to apply it. That's why I feel it's very important to get a good solid foundation of understanding of what a derivative is before we move on to the computational aspects of how to actually compute them and do the maths behind them. So this lecture, in long story short, is going to be about understanding the derivative conceptually and intuitively. Now enough daddling about, let's move on to the meat of the concept, the derivative. Now if you were to ask me to give you a one sentence definition for what a derivative is, I'll probably say this. The derivative of a function, let's say f of x, is another function f prime of x, we use this notation, which describes the rate of change of f of x at different points. I'll repeat. So the derivative of a function f of x, so the derivative is something you do to a function, is another function f prime of x, so it itself is another function, which describes the rate of change of f of x at different points. What this definition is saying is that if I have some function f of x, its derivative is another function, it's just another function, f prime of x, but the value of this new function, the derivative, is the rate of change of f of x at different points. Right? That's what this is saying. So the value of f prime of x at different points x is simply the rate of change of f of x at that point. Right? So f prime of 2 is the rate of change of f of x at x is equal to 2. Now if you're still slightly confused or not fully comfortable with this definition, don't worry. We're going to be picking this definition apart piece by piece throughout this lecture, and this entire lecture is going to be about better understanding and comprehending this definition of what a derivative is. Okay, with that being said, let's now look at some functions to get a semblance of what rate of change might be, what this function f prime of x might be. Let's start off with some simple functions and work our way up from there. So let's say I have a function f of x is equal to 2x, and let's say I have another function, it's called g of x, and let's say that's equal to 10x, right? So f of x is equal to 2x, whatever input I give to the function, my output will be double, right? So f of 3 would be 6 for example, and g of x is 10x, so whatever input I give to the function, the output will be 10 times that input, 10x. Okay, now I'm just going to, for both of these functions, plot a short table of values of x and the values of the function, right? And what I want to do is I want to observe how these values change, right? So at x is equal to 0, f of x is just equal to 0. At x is equal to 1, it's equal to 2. At 2, it's equal to 4. And then 6, at 3, 8, at 4, and 10, at 5. So we go 0, 2, 4, 6, 8, 10. We're growing at a respectable pace. And the first thing notice that we're growing, right? We're getting bigger. We go from 0 to 10. Each value is getting successively bigger. So the function is growing. Second thing you notice, it's growing at a respectable pace. We're going pretty fast. We're going 0, 2, 4, 8. We're going respectably fast. Now let's turn our attention to g of x, right? Same thing, when x is equal to 0, g of x is equal to 0, but when x is equal to 1, g of x is equal to 10. When x is equal to 2, g of x is equal to 20. When x is equal to 3, 30, 40, 50, and so on. So while both of these functions do grow, even this one is getting bigger, this one's growing seems to be growing much faster. We're going 0, 10, 20, 30 versus 0, 2, 4, 6, right? These values seem to be getting bigger a lot faster as compared to these ones. So I could say that this one is growing fast, but this one is growing faster, right? Because the values are getting bigger faster, right? And now, okay, so this is fairly obvious, I'm sure, to most of you here. But let's take a step back and realize, what did I do? What was I looking at? I was not looking at the value of the function. I was looking at how fast was the function growing. How fast were the values getting bigger and bigger and bigger, right? And I concluded that while this function is growing fast, this function g of x is growing faster than this function f of x. So there is something to be said about the sort of rate of growth of a function. We can also think about this graphically, maybe to get a better understanding. So when we graph functions on the Cartesian plane, it's common knowledge that the slope of the resulting curve or the slope of the resulting line, right, that is its gradient, represents its rate of growth or rate of change, right? And I can just graph both of these functions on separate sets of axes, and you can immediately see that this function g of x is equal to 10x has a much steeper slope, right? It has a much greater gradient as compared to f of x is equal to 2x, right? It has a much steeper slope than this. So I can once again make the same conclusions that because this has a larger gradient, right, then it must be growing faster. Its values are increasing faster. It has a greater rate of growth. Right now I'm using some terminology. Rate of growth is how fast the function is growing. In fact, let's not call it rate of growth, because growth specifies the functions getting bigger and bigger and bigger. Some functions don't get bigger, they stay the same. Some functions get, like 1 upon x for example, will get smaller as x gets larger. So let's, instead of not call it rate of growth, we could probably call it rate of change, because we're not only talking about growing, we're talking about change of any kind. Functions can change, right? So instead of, from this point on, I won't say rate of growth, I'll say rate of change. And I can see that this function g of x is changing faster than this function f of x. It's growing faster, changing faster, same thing. It has a higher rate of growth than f of x, right? And once again, graphically speaking, it's because its gradient is larger, and we also looked at some values to corroborate this. So the reason I was going through this example was to get an understanding of what rate of change might be. It's the rate at which the function is changing. In this case, growing, could be decreasing, we don't know. So now we got this idea of rate of change. It's a measure of how fast the function changes, but how can we actually measure it, right? Like, sure, I've been talking in the air that, okay, this one's growing faster than this, sort of qualitatively reasoning about it, but how can I quantitatively come up with a method of measuring the sort of rate of change, how fast the function changes? Well, we actually have a simple formula for this. It's in fact the same as the gradient formula, and that is the change in f of x divided by the change in x. This, also you can call it delta f by delta x, is our rate of change. It tells us how fast the function is growing. So we take a change in f of x and we divide that by the corresponding change in x. That tells us how fast the function is growing. It gives us a number to measure its rate of growth or decrease. As I said, it gives us a number to measure its rate of change, right? Now if you want to, delta f by delta x is slightly ambiguous, so we could write it, we split it up into taking 2 points, x2 and x1, and we just take the difference of the value of the function to get a change in f of x, and the difference between the values of points to get change in x, right? This is another way of writing the exact same thing, right? So we've got the change in f of x divided by the change in x, right? And this will tell me the rate of change between 2 points of our function. How fast the function is growing or shrinking between these two paths. Now, when we apply this formula, it will give us a number. It will just give us a straight number, right? 4, 5, 7, minus 2, something, right? Now, you might think, okay, well, what is this number? It is simply the amount that f of x changes per unit increase in x. This formula allows us to compute the amount that f of x changes per unit increase in x. That means that if I increase x by 1, what is the corresponding increase or decrease in f of x, right? If I increase x by 1, what is the corresponding increase or decrease in f of x? Now think about it. This is exactly what rate of change is. If I increase by x by 1 and f of x increases by 10 or 15 or like some really big number, right? Then the rate of change is pretty high, only one change in x and f of x goes up by 10. The function is changing pretty fast. But if I say when I increase x by 1, the function only increases by half or a quarter, but then the function is increasing very slowly. Every one change in x, the function only goes up barely by a half, right? So this number, the amount that f of x changes per unit increase in x is a good way for us to measure the rate of change. If you're still slightly uncomfortable with this idea of measuring rate of change, right, it's very easy to sort of conceptualize it if we draw an analogy to a car moving, right? Now, let's say a car is moving, and I can define a function, it's called that s of t, which tells me its distance it has traveled at any point in time, right? So s of 5 will be how much distance is traveled after 5 seconds, s of 10 is how much is traveled after 10 seconds. So I've defined a function which tells me how much distance the car has traveled after t seconds, right? Now, what is the rate of change of this function? That is simply the speed of the car, right? Rate of change, how fast is the distance growing per unit time? That is exactly what speed is, right? So the rate of change of this distance function is just going to be the speed of the car. It's how fast the distance is increasing, how fast the distance traveled is growing, right? And how do we measure speed? In meters per second. We're seeing how much distance is the car traversing per unit time. How much distance does the car traverse in 1 second? And that tells us, that gives us a good understanding of how fast the car is moving, how much its distance is changing, how fast its distance is changing, right? So hopefully thinking about, speed might give you a good analogy for rate of change. But of course, that's only one example. You don't have to thinking about that. What I want you to take away is we measure rate of change using this formula, and all it's telling us is how much f of x changes per unit increase in x. I'm sure many of you must be very familiar with this, but I wanted to get this out of the way before the lecture just to make sure that it's very clear to everyone present. Okay, and I think we can look at some better examples to get a good idea. So when f of x is equal to 2x, I can just apply this between any 2 points. Let's just take 2 and 1, right? I'll take the value of the function, the change, and then the value of x, the change. So 4 minus 2 over 2 minus 1, that's just equal to 2. Now once again, what is this number 2 telling me? This number 2 is telling me that this function is growing at a rate such that 1 increase in x corresponds to an increase in 2 in f of x. For every time I increase x by 1, f of x increases by 2. So 2 units per unit, you could say, right? And when we look at the functions on the table, it makes perfect sense. As I increase x by 1, f of x increases by 2. 3 to 4, 6 to 8, right? Every time I increase x by 1, f of x increases by 2, right? And this number 2 is giving us a good way of quantitatively measuring how fast this function is growing by saying how much is f of x increasing per unit increase in x. Now let's have a look at g of x, because this is 10x, right? We'll apply the same formula, right? We'll take 2 points, once again same 2 points, 2 and 1, right? So we get 20 minus 10 this time, and upon 1, this is 10, right? Now 10. This was 2, this is 2 units per unit, this is 10 units per unit. What does this number mean? It just means that for every increase in x, unit increase in x, the function increases by 10. So as I increase x by 1, the function instead of increasing by 2, is increasing by 10. So it's growing much faster. Once again, we can easily see this as I increase x by 1, g of x increases by 10. X by 1, 3 to 4, 30 to 40, right? It's increasing by 10 each time I increase x by 1. And because this is increasing, I can see that this is growing much faster than this. This is now a quantitative way to show that the rate of change here is 10 units per unit, whereas the rate of change here is 2 units per unit. So I can say this one is growing faster than this, right? This is just a way for us to measure the rate of change of functions. We can use this formula to figure them out, right? Okay, so please, this is a very important part of the lecture. This is all the basics of the idea sort of laid out. Please pause and ponder or rewind if you're online, and try to get a better understanding of what I talked about here if in case you're uncomfortable with anything, because now we're going to be going into slightly more uncharted territories and talking about some slightly more funky concepts until we finally reach the idea of a derivative. So please make sure that at this point you're comfortable with everything I've covered. These are just ways to measure rate of change, and this is how we do it. So I'm assuming if you're online, that is, you've done that, and we can move on. So here's the thing, I haven't been perfectly honest, or I've been pretty selective with the functions I'm choosing. And that is that they have a constant rate of change, right? So I could just say that the rate of change of f of x is equal to 2x is 2. That means for every increase in x per unit increase, the function increases by 2. I could say that. For 10x, right, same thing. It's got a constant rate of change of 10, right? So for every time I increase x by 1, the value of the function increases by 10. Right? So there are constant rate of change. They don't change for the function. The function grows at a steady rate. It's not growing faster or slower in some places. It's steady, right? And it's a constant number. But the majority of functions out there aren't like this. They grow fast in some places, slow in other, then fast again, then slow again, then they won't grow at all, right? There is no limit to the amount of funky functions that you'll find out in the world, right? Which grow at different rates, right? So let's take an example. Let's take now f and g. Let's take z of x is equal to x squared, right? This is a slightly different function from what we've been dealing with before. Once again, I'll plot this, and let's just have a look at how this function is growing. So we go from 0 to 1, 0 to 1, then to 4, then to 9, then to 16, then to 25, right? Now, of course, the function is growing. It's growing pretty fast, but what I want you to pick up is that its rate of growth is also increasing, right? Initially, we go only going from 0 to 1, and then 1 to 4. But then we go from 4 to 9, and then 9 to 16, and then 16 to 25. It's getting bigger, faster. A good way to see this is just by seeing, initially we go up by 1, then we go up by 3, then we go up by 5, and then 7, and then 9, right? The amount we are increasing per unit x is itself increasing. It keeps on getting larger and larger and larger and larger. It is what we call accelerated growth. It's growing faster and faster and faster and faster, right? So that's the case of x squared. It does not have a constant rate of change. It starts off very slow, 1, 4, but then it accelerates 9, 16, 25, right? And if you want to look at one thing about this graphically, we can have a look at the graph. Now, I want you to recall the previous two graphs we were looking at were lines. And what that signified was that they had a constant rate of change. That they were not growing fast or slow. They were just a straight line. The slope was constant. We had a constant rate of change. Now look at this. Would you say the slope was constant here? No. It seems to be growing very slowly. It seems to be growing faster and faster and faster and faster. Almost exponentially. Right? Once again, when we graph functions, the rate of growth or the rate of change is given by their slope. So you can see at this point, the slope looks something like this. Right? If I draw a tangent line, it looks something like this. Right? But if I draw a point at this, the slope looks completely different. It's much steeper. So I can see that the rate of change has increased from this to this. Right? So we can see that at different points, the rate of change of the function is different. It's not the same. We can't just use one number to describe it anymore. Now here's where I want to point out something to be cautionary of. Many people will try to tell you that the slope of the tangent line on a curve, which is what these lines are, or line segments are for that matter, is a derivative. That's what a derivative is, just the slope of the tangent line on a curve. My God, I won't tell you how many times I've heard this. This is not a good definition of derivative. It's factually correct, but don't get too attached to this idea that this is what a derivative is. No. A derivative is a function which tells you the rate of change at different points. It's not necessarily the slope of a tangent line. Don't get too attached to this idea because it's very limiting in what it is. Derivatives don't have anything intrinsically to do with graphs. Just think about that. It's useful to use graphs for these sort of visualizations. We are able to latch onto them much better, but don't get too attached to the idea is all I'm saying, right? But hopefully overall you can see that I've demonstrated that the rate of change of x squared itself is changing. It's different at different points. The growth is accelerated growth. It's getting faster and faster and faster. Once again, we can draw an analogy to a car, right? Does a car always have to move at a constant speed? Absolutely not. Imagine you're punching it on the highway. What are you doing? You're getting faster and faster and faster and faster. So your speed, which remember was our rate of change, is also increasing. It itself is increasing, right? So if you're getting faster and faster and faster and faster. And when you're on a car ride, you're not traveling at constant speed. Sometimes you'll be getting faster, then slower, then you'll grind to a halt, then you get faster again, you'll accelerate, you'll decelerate, right? So the speed also changes. That is, the rate of change also changes. So my point is that in the majority of functions you're going to encounter, the rate of change itself changes throughout the function. It's different at different points, right? So now, if that concept is synced in, we can move on to think about, well, now how do we define a measure rate of change? So earlier, right, I could say that, okay, f of x is equal to 2x, so the rate of change of f of x is 2. A simple number, and I'm able to give it to you. But now, if I've got some other function like x squared, how do I define the rate of change of x squared? I can't just give you a number anymore because it's different at different points, right? Here it might be 2, there it might be 4, there it might be 9, right? It could be different at different points. So how do I tell you in one sentence what the rate of change of x squared is? So a number doesn't seem to be a good way to describe rate of change anymore. So I want you to pause the video. Given that the rate of change itself is different at different points on the function, what might be a good mathematical tool to describe rate of change? Right? If you're watching online, please pause the video. I'll give 2-3 seconds for the people present here in the hall. Please just think about this. It's very important because the thinking you do for yourself will give you the best learning. If the rate of change itself is different at different points in the function, what mathematical infrastructure might we use to describe it? And well, the answer is another function. It's literally the purpose of a function. So because the rate of change itself is different at different points in the function, let's not give it, just assign it a number because it's different for different points. Let's give it a function, and the value of that function will tell me what the rate of change of my original function at that point is, right? So I'll just define another function which will tell me the rate of change of x squared for different points. So I can figure out that at x is equal to 2, what it is going to be, at x is equal to 5, what it's going to be, and so on and so forth, right? So if it's different at different points, just use a function to describe it instead of a number, right? And that way we can describe every function under the sun, right? Because we can, even if its rate of change is different, a function can output different values. So once again, instead of using a number, we're now going to use a function to describe the rate of change, because the rate of change itself is changing throughout the function, the original one I mean. And this is exactly, you'll recall, what a derivative is. So now you might want to think about what this function's output would be. What will this function's output be, right? What will this function's output be? Well, it's going to be the rate of change in and around a particular point. So rate of change is different for different points. Normally we measure rate of change between 2 points, right? Between x2 and x1. But if the rate of change itself is changing, we can't do that anymore. So instead, we're going to measure it in and around a given point. So at x is equal to 2, in and around x is equal to 2, what is the rate of change of the function, right? Or at x is equal to 4, in and around x is equal to 4, what is the rate of change, right? So this is what the output of that function might be, right? So what is this rate of change? It is the rate of change in and around different points, right? That's the way to conceptualize it. So let's revisit this idea of the derivative, and hopefully at this point this definition becomes slightly clearer. So if I take a function, if I take the derivative of that function, it's just another function, right? And the value of this function f prime of x, we write this as the derivative of f prime of x, right? This is a standard notation. The value of this function is just the rate of change of f of x in and around different points. So if I put x is equal to 2 here, right? F prime of 2 is the rate of change of f of x in and around the point x is equal to 2. Not between 2 and 5 or 2 and 7. In and around that specific point, how fast is the function growing or shrinking? How fast is the function changing, right? F prime of minus 1 is around, in and around the point x is equal to minus 1. How fast is the function changing, right? What is its rate of change? So this function, this derivative, is just outputting the rate of change of f of x. Nothing else, nothing more, right? Nothing more, nothing less. That's what it is. It is just the rate of change of f of x in and around these different points. That's all a derivative is at the end of the day. So let's look at an example just to get a better understanding, right? So we'll return to x squared. Now I happen to know for a fact that the derivative of x squared, we write this as z prime of x, is 2x. I happen to know this for a fact. We'll be investigating why in future lectures, but I just happen to know that for z of x is equal to x squared, the derivative is 2x. What does this mean? Just to reiterate one more time, just to make sure this idea fully sinks in, that the rate of change of x squared, it can be described by the function 2x, right? So at any point x, the rate of change of the function x squared in and around that point will be 2 times that point, right? Will be denoted by this function. So this function tells me the rate of change of x squared in and around different values x, right? So z prime of 2 is 2 is equal to 4, right? What that tells me is that in and around the point 2, x squared is growing at a rate of 4 units per unit. Approximately in and around that point, x squared is growing at a rate of 4 units per unit. At 0, z prime of 0 is going to be 2 to 0, the rate of change is 0. The function is not growing at all. So at x is equal to 0, there is the 0 rate of change, right? In and around the point x is equal to 0, there is no rate of change. Z prime of 7, 2 into 7 is equal to 14. What this means is that at x is equal to 7, the function x squared is growing at a rate of 14 units per unit. In and around that point, it is growing at a rate of 14 units per unit. At 114, you can go as far as you like, right? 114, 214, 228. So at the point 214, x is equal to 114, this function x squared is growing at the ludicrously high rate of 228 units per unit. It's growing very, very, very fast in and around that point. So in and around these different points, that's how it's going. So this is just the rate of change of x squared. All these are the rate of change of x squared at different points in and around different points. I like this phrase in and around because it sort of clears up what it is. Many people get uncomfortable with the idea of the derivative at a point. It's just the rate of change in and around these different points. So in and around 0 is 0, 114 to 120. That's all that it is, right? This is what a derivative is at the end of the day. Okay. Now this was a very long, very slow lecture, very drawn out, but it was done on purpose to make sure that this is very clear, right? To make sure that this concept of what a derivative is very clear before we venture into sort of mathematically describing it. And that's what you might be wondering, right? Like, this is all fine and good. You told me what the derivative is and I can calculate the values, but how might we get derivatives? And why is 2x a derivative of x squared, right? How would we compute these values in and around a point? The formulas we use in class are only between 2 points. How can I create a formula for at a single point, right? These are all questions which are probably flooding your head. How do I mathematically describe a derivative? What mathematical infrastructure can I use to actually take derivatives of functions, right? As I've done here. That's going to be the topic of my next lecture. Lecture 2 will be about understanding what mathematical infrastructure we use to take these derivatives, to find these rate of change in and around different points, to get these functions, right? That's what the second lecture is going to be about. But this lecture was just making sure you have a solid foundation of the understanding of what a derivative is. It's just another function which describes the rate of change of the previous function in and around different points. I've said that line so many times. One final example, if you will, is that if z of x is describing my distance, is a function describing my distance, the distance a car travels, for example, then z prime of x will be a function describing the speed of the car, right? That's the final thing which should hopefully make this concept as clear as possible. If this is distance, and that's the speed, right? Both functions. Okay. And that's all I really have for this lecture. Hopefully, you've taken away something of value, you've better understood what a derivative is. I've gone as slowly as possible just to make sure that the concept is reinforced to the maximum possible extent. And with that being said, I thank you all for attending this lecture. And I will see you all next week with lecture number 2, differentiation by definition.